Properties of negative feedback, and ultimately it is explaining the advantages what we discussed earlier of a negative feedback. Okay, first one is gain desensitivity. Okay, now in this again it's going to prove ultimately at last. You can see here. Okay, let me start from the beginning only. So AF is a feedback, amplifier feedback with amplifier gain with feedback is equal to A by 1 plus A beta, general expression. I am now going to differentiate this. I am going to differentiate this with respect to A. I am going to take differentiation of AF with respect to open loop gain A, and we know that this is in the form of A by B. Okay, division rule you need to apply, right? So that is you need to keep one parameter as it is, and you need to differentiate other minus, alternately you have to do other one, divided by denominator should be taken square, right? It is something like A differentiation of B minus B differentiation of A divided by B square. Okay, so once you solve for this, you get this. Okay, once you apply differentiation, you get this. A beta will get cancelled, right? You left with 1, so this it is reduced to this, and you can split it like this. Okay, because it is square, you can split it. Okay, and 1 over 1 plus A beta is nothing but AF by A, because A by 1 plus A beta is equal to AF. So AF, if you take A to the denominator, it becomes AF by A. So it is AF by A into 1 by 1 plus A beta. Okay, now I'm going to swap these two. I'm going to swap these two, right? You can see AF is here and A is here. Okay, in order to say that any change in output gain with feedback is reduced by a factor of 1 plus A beta compared to the change in gain, open loop gain A. So percentage change in AF, that is due to variation in some circuit parameter, is smaller than the percentage change in A by a factor equal amount of feedback, by a factor equal to the amount of feedback. This is already proved in the previous problem. This is what we discussed in the earlier problem, right? So we proved it. Again, it is shown with some few derivation of few steps, right? This is what it is, gain desensitivity. Gain is not really sensitive. Gain is not sensitive to the changes in the parameters. Okay, that is what this derivation is actually speaking. Okay. Bandwidth extension. Please refer this diagram. Okay, this is the frequency response curve drawn frequency versus gain, right? This is the frequency response. You can see this is the flat one. This is the gain, maximum gain, right? And this dark or black response, what we are seeing, it is a gain, frequency response without feedback, right? Without feedback. And this is the gain, blue colored. This is the frequency response of an amplifier with feedback. So your gain is reduced by this amount. Gain is in terms of dB, decibels, it is 20 log 1 plus AM by B. 1 plus A beta, right? 1 plus A beta, that is the value by which it is reduced. You can see here, right? Or you can see here, right? A by 1 plus A beta, this is by this amount, AF will be reduced compared to A, right? So what is that? This is, right? So gain will reduce. If you have a feedback, definitely gain reduces. Earlier it may be somewhere around 60 here, say 100, now it becomes 60. So if you have a negative feedback, gain definitely will reduce. It is a disadvantage, but you can observe here the bandwidth is increased. Earlier without feedback it is FH minus FL, right? So this is the bandwidth. Okay, now if we have a feedback, then gain will reduce, of course, like this, gain will reduce. Okay, gain will reduce, but bandwidth increases. It is FHF minus FLH. See, the bandwidth is increase in bandwidth by the same amount. The amount by which it is reduced, by the same amount your bandwidth increases on either side. So that is the advantage part of the negative feedback. Okay. So this is what bandwidth extension is all about. Now interference interference reduction. For that, let's see one diagram. Okay, so here you can see this is a diagram where we don't have any feedback in this amplifier. So A1 is the open loop gain of the amplifier. Input is Vs, output is V0. Okay, we have one more input here. We call it as Vn. Okay, it is a noise voltage. Okay, it is a noise voltage. It is an interference, unwanted signal. Okay, it is there because of external noise or maybe internal to the system, whatever it may be, but ultimately it is an unwanted thing. So the parameter called signal to noise ratio or signal to interference ratio, ratio S by I. Okay, this is the parameter by which one can measure the performance of the system, okay, in terms of its interference. Okay, how better the system to remove the interferences. Okay, so better system removes the interference. Okay, that is measured by signal to interference ratio. Okay, so it is Vs by Vn. It is Vs by actual input to the noise input, Vs by Vn, and value of which must be always more. Okay, more the value of signal to interference ratio, better the system performance. That is what it says, right? How I see Vs is in the numerator, Vn in the denominator. If Vn is reduces, means noise reduces, S by I increases, the ratio of which increases because it is in the denominator, right? So it is inversely proportional to the noise, right? So ultimately the aim is to increase the signal to interference ratio, right? Okay. If you don't have feedback, it straightly depends on this Vn, right? If more Vn, less the signal to interference ratio, lesser the performance, right? Lesser the noise, better the performance, right? It is a straight equation. It is a straight equation. Okay, now see the below diagram, this one. We have two stages here, assume A2 and A1, and we have a feedback system here, output to the input. Okay, so two stage, please remember. And in the first stage you can see there is no interference introduced here, and at the second stage there is an interference or noise called Vn. Okay, and this is beta, which is a feedback gain, right? So you can see the equation, output equation. V0 is equal to Vs A1 A2 by 1 plus A1 A2 beta. This is just like A by 1 plus A beta. Okay, and output, this is the output voltage because of the input Vs, output of the system. Okay, this V0 is equal to Vs into A1 A2 by A1 plus A1 A2 beta. This first term in this equation, it is the output voltage V0 due to Vs. This second term, okay, Vn into A1 by 1 plus A1 A2 beta. This second term is the output voltage V0 because of Vn alone. Because of Vn alone. Whether it is A2 or A1, feedback remains same. That is why the denominator remains same. Amount of feedback 1 plus A beta remains same. It is A1 A2 A1 A2. But in the numerator, so when we consider this as an input, ignoring this, then it is A1 which come into picture, right? So when you consider Vs, you cannot say you should consider A2 alone, because it has to pass through this A1 also, right? So it is A1 A2. So ultimately, if you take a ratio of Vs by Vn, considering this, okay, all these parameters will get cancelled. Only the A2 term is remain. Okay, will remain as it is, because both are same. If you take Vs by Vn ratio, okay, all these terms will get cancelled. You left with only A2. So signal to interference ratio is increased by A2 value, okay, compared to this original or basic equation, you can see signal to interference ratio will be increased by A2 if you have a feedback system. If you have a feedback system, something like this. So more the value of S by I, better the system. It means it eliminates interference. Right? That is what it is suggesting there. Okay. Right? That is how it reduces the interference. That is, it is one of the advantage of having a negative feedback. Okay. Now reduction in nonlinear distortion. You can see this transfer characteristic of an amplifier. A, that is a transfer characteristics here, this one, it is A, it is an amplifier without feedback, and this transfer characteristics is for amplifier with feedback. You can see the difference. It is almost looks like linear, okay, and this is not really linear, okay. So there is more changes or sudden changes in the curve, and it is of course piecewise linear characteristics curve here. Okay, we have applied a piecewise linear characteristics here, and see the difference. This is the non-linear one, and this is more like a linear. At any change in this input, equally change in the output. Right? Fine. So see here, example, for a change in A, from 1000 to 100, right, if I change a gain of an open loop gain A of an amplifier from 1000 to 100, right, feedback gain or gain with feedback will be changing from 90.9 to 50. If A is equal to 1000, AF becomes 90.9. If A becomes 100, 10 times reduced, okay, right, then AF becomes 50. Now it is not reduced by 10 times, right? 90.9 becomes only 50. It is not 9, so that you can say it is 10 times reduced. No, right? So that is how it maintains the linearity. Okay, so that is how it avoids non-linear distortions. Okay, so this is the end of the lecture 1. So we'll continue with the feedback amplifier in the next lecture. Thank you.